Thanks, everybody. Can you hear me okay in the back? Okay, I'm pretty loud. So for a little bit of something different, my take on causality adjacent issues as it pertains to learning for people. So here's the setup. Okay, think about this. This is the Jingo arm. Let's say I bring it in your home and it's helping you unload the dishwasher. So the way this robot would work, if I shipped it right now, would be it will run some sort of optimization, reinforcement learning, trajectory optimization, whatever it is, to come up with a policy or a trajectory that does some optimization of a root function. We would probably do something like give the robot access, try to give the robot access to certain things that we know are going to be important when this robot is in your home. Like we might say, look at the cup orientation if you're carrying an object so that you don't spill stuff. We might say, make sure you give good clearances to objects like the table and the walls and so on. Don't get too close because you might collide. And of course, try to be efficient and so on and so forth. So we think of these as features. And then we might ship the robot. We might kind of try to carefully tune these trade-offs on these features, maybe some of them end up as constraints, whatever. The details aren't important, but we try kind of tell the robot this is how these things combine into a combined function. And then the robot goes off and optimizes for that. And it ends up with some trajectory where it's sort of, you know, carrying and you see that represented. Now, this is our end user. And I should say, this is Andrea. I don't know if you saw my first slide. But everything I'm talking about today is really the work of my student, Andrea Bo. She's not my student anymore, actually. She just graduated. She's faculty at MIT. But this is her story, not mine. I'm just kind of the person putting the words out here. So imagine that, Andrea's playing the user here. The user cares about these features too, but maybe as they look and see the robot keeping this cup so high up, they might get concerned that if it drops it, it will break. So they might actually prefer that the robot actually keep things closer to the ground. And so, what Andrea might do is tell the robot something or intervene and push on the robot and get it to be closer to the ground, closer to the table. And before Andrea joined the lab, some of the work we had done was looking at the problem of how should the robot respond to this kind of input from the person? Because if you're doing something that you think is optimal and your user comes and corrects you, clearly what you're doing wasn't optimal, right? Clearly you have the wrong notion of optimality. So we worked a lot on this notion of, okay, we might ship the robot with some reward function, but that's not the ground truth. What the person wants is the ground truth. It's in their head. So how can we learn from this type of corrections from the user and adjust our notion of optimality, adjust the objective? So this was some work that had happened where the robot looks at this correction, reasons about what sort of modification of the reward function is that optimal under, and learns a sort of a different reward function, our theta prime, and then it goes and optimizes that, and lo and behold, it keeps the cup closer to the table. Now, the reason this works is because it very much relies on this set of features and this set of features being the same. Right? The robot knows what's important. The robot already knows that distance table is a thing that the person might care about. And when the person pushes the robot down, it has a chance of saying, oh, these are not the trade-offs you want different trade-offs. The problem that Andrea looked at is how on earth is the robot going to get these features? Because realistically, I can't guess them, right? And program everything that you as the end user might care about. So, and she likes to give this example that I think Allison probably knows, or probably even she was the person who did this experiment, with kids, and how, our robots kind of get shipped almost as like in bad ways, not in ways that Allison likes, but in bad ways, get shipped as sort of like 3-year-olds that are 4-year-olds, where they don't actually know about everything that matters in order to solve the tasks that they need to solve. So, here's a cute little example. We don't have a mic. We have a mic here.
The same. Okay.
So are these the same? The same.
Is this or are they the same? That one has more words, so why is that?
Because it's stretched out. So you have a task to do, and the kiddo has features, right? It's just, and they kind of correlate with the answer, but they're not causal, right? This is not the actual causal feature determining what the length is not the thing that actually determines how many quarters are there. Similar with this is fun, so let me show it.
Does this glass have more water? Does this glass have more water, or are they the same?
Ooh, let's see. Okay, so glorious. So robots are like this. There's no way that they'll actually have all the right features that capture what we as people really care about. And I'll show you one example of the robot completely missing something. So here we set it up where it's the same thing as before, but now Andrea doesn't want the robot to get too close to her. The robot is too much in her personal space, and she has these proxemics preferences, but notice there's no feature here that talks about proxemics. And so when we try to apply that same algorithm that was beautifully reacting to Andrea's correction and sort of adjusting the reward function, things don't go so well. So there's this distance from the person that matters now, and Andrea pushes the robot away from her. But when she lets go, the robot does this learning update, right? Trying to say, well, what is this push about? And there's no feature on distance from her, so the robot can't really explain the correction that way. However, accidentally what happened was when Andrea pushed the robot away from her, she also brought the robot a little bit closer to the table. So the robot's like, aha, I know what you want. Let me, make sure I get nice and close to you again, because, that's the optimal. But let me go closer to the table, because that's what you told me. And so we call this representation misalignment. The representation internal to the person that they care about is different from the representation that the robot is using for understanding the reward function. To correctly interpret people's input, you need to have representations that are the ones that people are using, and we call this the representation alignment problem. And so what Andrea has been asking her PhD thesis is, how can robots align the representation with the human that they're learning from, or with their end users more? And so let's have a look at an example that's sort of similar, and so I can share with you sort of the naive thing to do that doesn't work, and sort of the thing that Andrea came up with, which works a little better, but still, I don't think that anyone has solved the problem of representation alignment, just to be clear. So we have a person here that cares about a bunch of things. There's a desk with a laptop on it, and the person, if I were to visualize this, what we're imagining the ground truth thing that the person wants, and visualizing this 3D space, it looks something like this, where you want to kind of get clearance from the table. You really don't want to be on top of the laptop, right? You don't want to be carrying things on top of the laptop. Nor about you, but I don't trust robots carrying cups of coffee on top of my head. Or my 2-year-old. There's, again, lots of similarities. So there's these regions where it's like, no, don't go there. It's okay to be there, and so on and so forth. Now on the right-hand side, we have a robot, and the robot doesn't know about this laptop business. Doesn't know that all people might actually not want, liquid spilled on their lap. And so what can the robot do? So one way to solve this problem is to say, well, I know some things, I don't know some other things. I'm going to represent what I don't know as a neural network. And I'm going to try to learn a reward function that maps from state to a scalar, so a reward function represented as a neural network. And I can do that. The traditional way to do that, to do reward learning, is through demonstrations. So this is a technique in robotics. It was popularized in AI by folks like Stuart Russell with Andrew Ng, and then Peter Abeel. It kind of dates all the way back to inverse optimal control and Kalman. But the enough notion is the person can give demonstrations of what's optimal behavior according to all the things that they care about. And the robot can try to figure out what reward function explains that behavior as optimal or approximately optimal. This is called inverse reinforcement learning. It's a misnomer. It's really inverse planning or inverse optimal control. But in any case, let's just say inverse reinforcement learning, the robot can try to come up with a reward function that explains those demonstrations as optimal. And so we tried this, Andrea tried this, collected a lot of demonstrations and fit a neural network, doing something called maximum entropy inverse reinforcement learning, which is kind of your default sort of deep learning inverse planning algorithm. And so this is what, if I am to visualize the reward, this is what it looks like. And it's a little bit hard to tell. I'll share with you the implication of this, but you'll notice there's similarity, right? It gets something about laptop and so on, right? So it's not complete madness, but the structure is somewhat different. Like it doesn't have this notion of on the laptop bad and then, you know, distance from the table. It has something that kind of goes this way or something like that. In general, our experience with these kind of algorithms, and it won't surprise you, is that even if you throw a lot of data at them, there's going to be spurious correlations in the data that sort of the neural net will pick up on and say, oh, that explains the thing that you're doing. I don't know if you've seen this example. Someone was doing it wasn't inverse reinforcement learning, which is behavior cloning for self-driving cars, but from like a dash cam image that would show the dashboard and outside. And if you train a policy based on human driving, what it learns to do is it learns that people only brake when the brake light on their dashboard comes on. That's kind of a glorious example of a spurious correlation. And it's you know, it's really hard to disentangle these things without actually going and probing the world and see what's going on. So here, because it tries to sort of, our conclusion is that IRL is trying to do too much. It takes these demonstrations, and these demonstrations are this combination of what the person cares about, how all these things that the person cares about combine, and how they then produce through planning or through reinforcement learning an optimal thing. And all you get is this end thing. You have to do all of this work of, well, what are the things that matter? And so of course it's going to be all an entangled mess. And it didn't go away as we tried to throw more data at it. So you end up, you know, you optimize the correct reward function, you get this, you optimize the learning reward function, you get this, or vice versa. I forget which one, but there's a difference. Okay, so instead, what seemed natural for us to do is to kind of divide and conquer here. So could we sort of break it down and say, can I learn about these things that are missing in absence of learning the full reward function? Is there some input I can get from the person that actually teaches me sort of what it is that they don't like about what I'm doing? In this case, like, oh, you gotta actually protect this laptop. Can I get some input about that? And afterwards, kind of combine it with everything else. And then maybe I get demonstrations that teach me how those things combine, but I already know what sort of the kind of core features that the person cares about are, or I do corrections or whatever. So what we thought is that instead of learning the representation implicitly by getting demonstrations or corrections or comparisons, the robot should sort of ask for input for human data that kind of explicitly targets the features separately that are important to the person. And then the question became, okay, we want to learn, kind of have the person teach us sort of separately, one by one, the features that they think matter in the task, but how do we do that? What is input? Like the whole robotics community works with demonstrations, maybe with comparisons, RLHF, blah, blah, blah. What do we do? Naively, what you could think of doing, if you're not a psychologist, if you're like a computer scientist, naively what you think of doing would be like, well, I want to learn this neural network that maps states to not the reward, but the feature value, the thing like the, are you on top of the laptop value? So I could kind of have the person try to say, well, this state corresponds to this feature value, and this state corresponds to this feature value, and so on and so forth. And then I could just do supervised learning to train this neural network. Of course, one problem is that you'd need a crap ton of labels to actually learn something useful here. The bigger problem is that people can't actually do that. It's not reasonable to ask people to look at states and say, 3.75, or even on a scale from 1 to 7, how good is this? So we need some informative inputs without actually placing too much cognitive burden on the person and having them coming up with an input that is actually kind of usable, it's reliable, it elicits reliable feedback from them. And what we came up with is this notion of asking for the person to guide the robot through states in a way that is monotonically increasing or decreasing in terms of the feature value that they're trying to train the robot through. So they give us something that we're calling a feature trace, where they take the robot and they put it in a state where the feature is very bad, and they kind of guide it out of that state. And we say try to do that in a way that's at least monotonically increasing, depending on. So sort of we expect that there's this relationship. That's what feature traces is. That's what it looks like. And so what we have people do when they want to teach the robot such a concept is, they do a few of these. I'm going to share a little bit with you if I have time about what set people come up with. And I found it very interesting. And then we train a neural network on that data. And the way we train a neural network on that data is by using this monotonicity assumption that we make, right? So we know that the states along the trajectory sort of have to, satisfy this property. If 5 comes after 1, then we know that the value of 5 is lower than the value of 1. And we use the typical like Boltzmann noisy rational assumption here, because people are obviously not perfect at doing that, and we want to account for that noise. And so we looked at this with people. We looked at this was during the pandemic. This is actually Andrea's bedroom. This is a table in her bedroom. She took the robot home, don't tell Berkeley, and she did this. And so we had to figure out how to evaluate this with people. And we sort of split it into evaluating it with Andrea, who's this expert, as expert of a user as it gets, knows exactly how the algorithm is going to work to interpret her input, and then evaluate it in simulation with people. So she had these Zoom calls with people where they would have an interface in simulation and kind of teleoperate the robot to give these feature traces. So with expert users, aka Andrea, what we I guess this is just the visualization of the learned reward function, but or the learned feature. What I'm going to do is I'm going to take these features and project them onto sort of the table surface. And so what you see here is an example of, here are some feature traces, and then here's sort of the learned feature. Qualitatively, this is the feature Andrea was going for. This is the feature that was learned. And we tried this across different features, and it's not perfect. But it seems to do kind of a good job with most of them, sort of localizing what is going on. I don't have a slide for this, but this proxemics one was interesting. So the proxemics one was, you want to teach the robot this notion of comfortable distance from you. And proxemics is an interesting one because I don't know about you, but I'm much more comfortable with the robot being, 20 centimeters from my face here, but a lot less comfortable with the robot being 20 centimeters from my face here. And so it's got this sort of, different shape to it, right? It's like an ellipsoid. It's like this interesting kind of covariance. And so what so Andrea was able to teach this, and I want to remind myself to tell you a little bit about what people did in order to teach this feature, because they were actually successful as well. From just Andrea's data, a few takeaways. One of them is that this is for different features, and at the end, with enough feature traces, you get something that has low error with respect to the ground truth you're trying to teach. The good news is that as you add more feature traces, you learn better. That's not surprising, but it's a good sanity check. And then the variance decreases, so kind of the quality of your feature traces is less important as you're accumulating more data. And then we tried it for reward learning, where basically on the one hand, you can do maximum entropy IRL. On the other hand, you could do this sort of separation into features that you're training and then putting it all together with just a few demonstrations or actually, I think Andrea tried a single correction. And qualitatively, these are some experiments where you kind of see this is the ground truth we were going for, this is what we obtained through this method, and this is the mess you obtained through directly trying to do it all at once. And then we looked at, well, can novices do this, right? Because it's a pretty complicated concept. I know how to do one, but how do I do multiple so that I cover the space in such a way that when the robot does its learning, it understands what the kind of the feature, the concept is. And so we did the user study, and people were not as good, obviously, than Andrea. That wasn't surprising, but their stuff seemed to still be pretty useful. And in particular, lead to really good rewards compared to a pretty strong baseline of doing the inverse reinforcement learning thing. So the maxent IRL, when maxent IRL was actually getting physical expert high quality demonstrations, whereas these ones were just from like user ones. So that was very reassuring. Let me skip over the subjective data and just maybe go back. Let me pause right here and explain this cool thing of how do people teach proxemics. So people figured out to do like a longer trace in the direction of where it's more okay, and a shorter trace in the direction where it's less okay. And we didn't tell them that, we didn't instruct them that. We figured out that would be a good way to teach it. I had no idea whether people would be able to get this. It was the kind of maybe the most complicated thing to figure out how to teach, and they did figure this out, most of them. So that was cool. So yeah, instead of learning the representation implicitly, we think that we should do this divide and conquer thing. We try to align with the person on what are the concepts that matter. And then figure out, okay, how do they combine? How do you want to trade them off? What are constraints? Maybe they're nonlinear, whatever combination you want. But let's kind of align first on what are the important aspects. And maybe I'll stop there because I'm running out of time. I'm not sure.
Yeah. I think that's very cool. What about before, in the time, say I'm unloading the dishwasher, and before I get so annoyed that I push the damn thing,
Yeah.
There might be signals for the robot. Are there signals for the robot before there that it's not doing well?
Yeah, I think there are. So not work that we've done, but there's some work from UT Austin that has looked at people grimacing, like the actual facial expressions, which I think are really good. Like before the robot is about to break something, go like, ugh! You might not even say something. You might not even say, we don't have it in us sometimes in these situations of panic to be like very rationally and collected. Please keep the thing higher up from the ground, or be careful, you might spill. But you might at least get a, and that can be really helpful. And I think in general, I'm of the opinion that people leak a lot of information about the things that they care about. So in the way that they react, in these corrections, in what they say, in the way that they do the task, which is then a demonstration on sort of their embodiment, not the robots. All of these are really useful sources of information. The most interesting one, if I have a minute to talk about this, is this work that with the advent of LLMs feels a lot less relevant, but Alison and I were talking about this at lunch. I used to be very concerned about this problem of if I tell the robot to clean up and the robot enters my room and sees my desk and I have a very nicely laid out house of cards. How is the robot gonna know that clean up doesn't mean clean up the house of cards? Less important now because you know who knows? GPT-4 knows that you shouldn't clean up the house of cards. So anyway, but before this, I had a student, Rohan, and he did this really interesting work on how even just seeing the house of cards should tell you what's important. So even the fact that people have been acting in the environment, you didn't get to see those actions necessarily, but they've been acting in the environment, and the state of the environment is a consequence of their actions. That means that even just seeing the state of the environment kind of leaks information about what people turn on. So we did some work on that. So there's a richness of signals, from gestures to reactions, to language, to corrections, to just how the way we've laid out our world, that I think can be informative.